on August 12th, 2026, the temperature in northern Spain is going to just plummet 10 degrees in a matter of seconds. The birds will stop singing, the wind will suddenly shift direction, and right in the middle of a late summer afternoon, the stars will actually come out. It's like the universe is going to casually reach down and just hit the lights.
Yeah, it really is the ultimate disruption of our environment. I mean, the sun rising and setting is, the most reliable rhythm of human existence. It's the baseline of our internal clocks.
Right.
So to have that rhythm abruptly suspended right in the middle of the day, it triggers this deeply visceral reaction, and not just in humans, but across entire ecosystems.
Wow, yeah. Well, welcome to today's deep dive. We're looking directly at the verified space agency data, astronomical reports, and observational guides for the highly anticipated August 12, 2026 total solar eclipse.
And there is an immense amount of physics operating behind the scenes to make this specific sequence of events even possible.
Exactly. So our mission today is to unpack the extreme mechanics of this celestial alignment.
Yeah.
We're going to look at the exact geometry carving this path across Europe and the Arctic, the back-to-back cosmic double feature happening that exact same week, and the brutal biological reality of why squinting at the sun will literally cook your retinas.
Yes, please do not do that.
We will get into all of that, plus the high-stakes science happening in the dark. And for you listening, whether you're actively booking flights to stand directly in the path of totality, or you're just planning to step out into your own backyard to look up, this deep dive is going to equip you with the precise knowledge you need.
We really want to focus on the hidden science here, the how and the why of what's going on over our heads.
Yeah, so let's start with the geographic reality of this event. I mean, we all know a solar eclipse is just the moon blocking the sun. But the sheer scale difference is what always gets me. The absolute darkest part of that shadow, the umbra, is just a microscopic moving dot on the Earth's surface.
It's incredibly small in the grand scheme of things.
Okay, let's unpack this. It's like shining a massive flashlight at a globe, but holding a little marble right in front of the lens. The absolute darkest part of that shadow is just a tiny moving dot on the map. If you aren't standing exactly where that dot drags across the Earth, you completely miss the main show.
What's fascinating here is the staggering precision required for that to happen, because the Earth is a rotating sphere, right? And the moon is moving along its own orbital trajectory at thousands of miles per hour.
Right, so nothing is standing still.
Exactly. That marble shadow doesn't just sit there. It gets dragged across the curvature of the planet at supersonic speeds. If the timing of the moon's orbit shifted by even a handful of minutes, or if the orbital inclination was altered by just a fraction of a degree, that shadow cone would completely miss the Earth.
Or it would just fall entirely over the open ocean where nobody would even see it.
Yeah, exactly. But for August 12th, 2026, the geometry favors some incredibly rugged and distinct terrain.
Yeah, I was looking at the path. The shadow makes landfall over the ice sheets of Greenland, sweeps across the volcanic landscapes of Iceland, clips northern Russia, races down over the open Atlantic Ocean, and then finally crosses into northern Spain in a small corner of Portugal right before sunset.
And that ending part of the path, in the Iberian Peninsula, it's particularly fascinating from an observational standpoint.
Because it's happening so late in the day.
Right. Because the shadow is hitting Spain and Portugal just as the Earth is rotating away from the sun, meaning sunset. The geometry of the shadow actually changes.
Oh, that makes sense.
Yeah, so in the middle of the day when the sun is directly overhead, the shadow is a relatively tight circle, but as the sun gets lower on the horizon, that shadow stretches out into this long, dramatic oval, and it moves much faster across the ground.
Wow. So observers in Spain won't even be looking up at the sky to see the eclipse, right? They'll be looking horizontally across the landscape.
Exactly. They'll be viewing totality through the thickest part of the Earth's atmosphere.
Which I imagine introduces completely different visual distortions. You get these deep twilight colors wrapping 360 degrees around the entire horizon. I mean, it's really no wonder there's a whole global community of eclipse chasers who plan international trips years in advance for this stuff.
It's highly addictive for a reason.
I bet. But I was reading the observer reports, and it seems like the most striking part of standing in that specific path of totality isn't just visual. It's that sudden, drastic drop in temperature I mentioned earlier. How does losing sunlight for just like 2 minutes cause the air to chill so violently?
Well, it comes down to how our atmosphere retains heat. The sun is constantly pumping shortwave radiation into the Earth's surface, which then radiates long-wave infrared heat back into the air.
Okay, so the ground heats the air.
Right. So when the moon's umbra races overhead at supersonic speed, it acts like a giant atmospheric shutter. It instantly cuts off that incoming solar radiation.
Boom, lights out.
Lights out, heat out. The ground immediately stops heating the air directly above it, and because the shadow is moving so incredibly fast, the surrounding air just doesn't have time to equalize.
So you get an abrupt, localized temperature crash.
You do, which changes the air density and suddenly alters the wind patterns. You are physically feeling the shadow of the moon wash over you.
You literally feel the mechanics of the solar system on your skin. That is wild.
It really is. But keep in mind, this only happens if you are firmly inside that narrow path of totality. If you are standing a few hundred miles outside of it, experiencing, say, an 80 or 90% partial eclipse, you miss these dramatic environmental shifts.
Because there's still too much sunlight.
Exactly. The ambient radiant energy of the sun is so overwhelmingly powerful that even 10% of its normal output is enough to keep the atmosphere relatively stable. The day looks surprisingly normal.
That is so counterintuitive, but it makes sense. Now, that same alignment, the moon sitting perfectly between us and the sun, showing us only its dark, unlit side, that triggers a massive secondary event that week, doesn't it?
It absolutely does. August 2026 is an incredibly stacked observing month. Because the eclipse coincides with a completely dark new moon, it sets up the perfect canvas for the Perseid meteor shower, which is peaking right in that exact same window.
Right, because August is traditionally an exceptional month for astronomy anyway, just because of the Perseids.
Yeah, and to understand why this double feature is so significant, we have to look at what a meteor shower actually is. I mean, it has nothing to do with shooting stars.
Right, they aren't actual stars falling.
No, not at all. The Earth is constantly orbiting the sun, and every August, our planet physically plows through a massive debris field left behind by a comet called Swift-Tuttle.
Okay, so it's essentially a cosmic dust cloud just sitting in our lane on the highway.
That is a great way to picture it. As the Earth rams into this debris field at roughly 67,000 miles per hour, those tiny fragments of rock and ice hit our upper atmosphere.
And they just burn up.
Well, they're moving so fast that they violently compress the air in front of them. That compression generates intense heat, vaporizing the meteor and creating those glowing trails of superheated plasma that we see from the ground.
Ah, okay. But the visibility of those plasma trails is highly dependent on lunar light pollution, right? Like normally if we hit that dust cloud during a bright full moon, the moon's surface reflects sunlight, its albedo, and it scatters all that light through our atmosphere.
Yes, the physics of that scattering is actually the exact same reason the sky is blue during the day. It's called Rayleigh scattering. When moonlight hits the gas molecules in our atmosphere, the light scatters in all directions, creating this bright ambient glow across the night sky.
Which I'm guessing completely washes out the fainter meteors.
Totally washes them out. The magnitude 4 and magnitude 5 meteors just disappear into the glow. In a normal year with a bright moon, you might only see the largest, brightest fireballs.
But in August 2026, the eclipse guarantees a perfectly dark new moon. The moon is showing us its shadow, meaning zero reflected sunlight and zero atmospheric scattering.
The sky becomes entirely transparent. This radically increases the hourly count of visible meteors. You're basically looking through a pristine, unpolluted window right at the Swift-Tuttle debris field.
Here's where it gets really interesting to me. Because the new moon kills the natural light pollution, does that mean these eclipse chasers flying to Iceland or Spain are essentially getting a back-to-back day and night cosmic show?
They absolutely are. And on top of that, planetary mechanics are aligning to make Venus exceptionally prominent and bright during this exact same window. It creates this heavily stacked 24-hour viewing period.
And that's a crucial takeaway for you listening. You don't have to fly to the coast of Spain to get value out of this event. During the day, you get the partial or total eclipse, and at night, thanks to the exact same lunar geometry, you get a maximized Perseid meteor shower.
It's an amazing opportunity for everyday sky watchers to just look up.
Yeah, but let's shift gears from the spectacle to the actual physical reality of observing the sun, because we really need to talk about safety.
Yes, we definitely do.
I was reading through the safety specifications for solar viewing, and I kind of want to push back on a huge misconception here. Because human nature says, hey, if the moon is covering 99% of the sun's surface during a deep partial eclipse, mathematically, we are only receiving 1% of the normal radiant energy.
Right, which sounds safe.
Exactly. So what does this all mean for the person who says, hey, The sun is 99% covered. It looks pretty dark out here. I could just squint and peek for a second,
Yeah.
right? I mean, how can 1% of sunlight instantly blind you when glancing at a sunset on a normal Tuesday doesn't?
It is a brilliant question, and the answer lies in a really dangerous combination of human biology and high-energy radiation.
Okay, break that down for us.
So when you look at a normal sunset, you are looking through thousands of miles of dense, lower atmosphere. That thick atmospheric wedge scatters and filters out most of the harmful ultraviolet and blue light before it ever reaches your eye.
But during a midday partial eclipse, the sun is high in the sky, so there's very little atmosphere filtering the light.
Exactly. And the ambient light is dropping rapidly, which actually tricks our eyes.
Oh, because it feels dark.
Right. That is the biological trap. Because the moon is blocking 99% of the visible light, the surrounding environment dims significantly. Your brain registers the darkness, and your autonomic nervous system responds by dilating your pupils wide open to gather more light.
Oh, wow. So your eye is actively lowering its own defenses.
Completely.
Yeah.
It is the worst possible response. With your pupil dilated, you look directly at that remaining 1% sliver of the sun. And that sliver is still emitting unscattered, highly concentrated ultraviolet and near-infrared radiation.
And it just goes straight in.
Straight in. Your wide-open pupil acts like a funnel. It takes that devastating high-energy light and focuses it directly onto the macula, which is the most sensitive central part of your retina.
And the most insidious part about this damage, solar retinopathy, is that it is entirely painless, isn't it?
It is entirely painless.
You could be staring at that sliver, literally destroying your central vision, and you wouldn't feel a single thing.
You wouldn't. The retina just does not contain nociceptors, which are the nerve endings responsible for transmitting pain signals to the brain.
That is terrifying.
It really is. And the damage happening isn't just a thermal burn like using a magnifying glass to scorch a leaf. It is photochemical toxicity.
Wait, so it's a chemical reaction, not a heat burn.
Exactly. The intense blue and ultraviolet light triggers a violent chemical reaction within the retinal pigment epithelium. It creates this flood of highly reactive oxygen molecules, free radicals, that literally tear apart the cellular structure of your photoreceptors.
Oh my God, so the cells are just breaking down on a molecular level.
Yes. And because you receive no pain warning to look away, the blind spots simply appear hours later, and by then the damage is permanent.
This is exactly why throwing on a pair of dark polarized sunglasses is completely useless. A lot of people assume that if the glasses make the sky look dark, they're safe.
They are absolutely not safe.
Right. Standard sunglasses, even the really expensive polarized ones, they're only designed to cut down on visible glare. They do virtually nothing to block the invisible infrared radiation that causes that photochemical destruction.
Standard sunglasses actually transmit thousands of times too much solar energy for safe viewing. You must use ISO-certified solar eclipse glasses.
No exceptions.
None. These are specially manufactured polymer filters, and they're coated with microscopic layers of aluminum or silver. They are engineered to block out 99.999% of visible intense light, and they completely reject the harmful ultraviolet and infrared wavelengths.
What about welding goggles? People always ask about those.
Standard welding goggles are also inadequate unless they are specifically rated at shade 12 or higher, which everyday hardware store goggles usually are not.
Okay, safety firmly established. Now,
Wow.
there is one and only one exception to the glasses rule, and it only applies to those standing firmly inside the path of totality, right?
Yes, the only time it is safe to remove those certified filters is during the brief 2-minute window when the sun's disk is 100% covered by the moon.
Full totality.
Right. Once the lunar landscape completely blocks the photosphere, which is the bright surface of the sun, the dangerous radiation is finally shielded. You can safely look at the completely eclipsed sun with the naked eye.
But the first microscopic bead of light reappears from behind a lunar mountain crater. The glasses must go back on immediately.
Immediately. And for anyone outside the totality path, viewing the partial phases, there is no safe window. The glasses never come off.
It's kind of ironic, honestly. The exact same biological mechanism that makes our eyes so vulnerable, the pupil dilating in the dark to let in more light, is exactly what astrophysicists are doing with their telescopes during those few minutes of totality.
That is a great comparison.
Right. They are throwing open their apertures to study the sun's outer atmosphere, the corona.
Exactly. The moon basically acts as a giant naturally occurring safety glass for our scientific instruments, or more accurately, a coronagraph.
Because usually the blinding brightness of the sun's main disk just completely washes out the corona.
Yeah, we can't see the delicate structure of the solar atmosphere from Earth because the source light is just too overwhelming.
It's essentially like trying to study a single firefly fluttering right next to a blinding stadium spotlight. You really can't do it until the universe temporarily hits the power switch on that spotlight.
This raises an important question, though, which is why scientists care so much about the corona in the first place.
Right, I was reading the research data on this, and the physics present a massive scientific mystery called the coronal heating problem.
Yes, it's one of the biggest puzzles in astrophysics.
On the surface, it makes absolutely no sense. The surface of the sun, the photosphere, is roughly 10,000 degrees Fahrenheit. But the corona, which is the wispy atmosphere extending millions of miles away from the surface, reaches millions of degrees.
It completely defies our everyday understanding of thermodynamics.
It's like walking away from a roaring campfire and finding out the air 10 feet away is somehow 1,000 times hotter than the fire itself.
Which is exactly why totality is so highly valued by scientists. It provides the only natural window to study the mechanics of that campfire.
So what are they actually doing during those 2 minutes?
Researchers deploy highly specialized spectrometers all along the path of totality. These instruments break the light from the corona down into individual spectral lines.
Okay.
By measuring the specific wavelengths emitted by highly ionized iron and calcium in the corona, scientists can map the exact temperatures and speeds of the plasma.
And the leading theory for this extreme heating involves the sun's magnetic field, correct?
Yes. You have to remember the sun isn't solid. It's a giant churning ball of electrically charged plasma. As this plasma rotates, it generates a deeply complex, twisted magnetic field. The theory is that these magnetic field lines get tangled up in the corona like twisted rubber bands. When the tension becomes too great, the magnetic lines snap and realign in a process called magnetic reconnection.
And that snap releases heat.
It releases an unfathomable amount of energy into the surrounding plasma, flash heating the corona to millions of degrees.
Wow. And this isn't just abstract astrophysics, right? That violent magnetic activity in the corona is what accelerates the solar wind. It literally dictates space weather.
Absolutely. When those magnetic bands snap, they can launch billions of tons of charged particles directly at Earth.
Which can interfere with our satellite constellations, disrupt GPS, and even overload terrestrial power grids. So our modern technological infrastructure is deeply vulnerable to the behavior of the corona.
Exactly. Yet scientists literally cannot collect this specific type of high-resolution intercoronal data in any other way from the ground.
So this beautiful tourist event basically becomes an incredibly high-stakes scientific mission.
A total scramble. Teams of astrophysicists from around the globe are rushing to align their sensors perfectly within that fleeting geographic path. They have roughly 2 to 3 minutes to gather years' worth of crucial atmospheric data before the sun reemerges and shuts the window.
That is incredible pressure.
Hmm.
Okay, let's pull all of this complex machinery together and rapidly distill the core takeaways for you listening.
Yeah.
First, August 12th, 2026, brings a geopolitically fascinating total solar eclipse driven by extreme cosmic geometry.
Right. The moon's shadow will sweep at supersonic speeds across Greenland, Iceland, northern Russia, and dive into Spain and Portugal right at sunset for a very dramatic horizon view.
Second, the mandatory new moon alignment creates a fully transparent, unpolluted night sky. That sets up a spectacular double feature with the Perseid meteor shower peaking concurrently, allowing you to see faint meteors that are usually washed out by atmospheric light scattering.
Third, and most importantly, your biological defenses will actively work against you during a partial eclipse. Do not trust your dilated pupils. Seriously. ISO-certified solar safety glasses are absolute necessities for all partial viewing phases to prevent silent, irreversible photochemical damage to your retinas. The only time you take them off is during the 100% full totality window, and that's only if you're lucky enough to be directly in the path.
And finally, this event offers a singular, irreplaceable window for scientists to utilize the moon as a giant optical shield. It allows them to study the magnetic mysteries of the corona, gathering data on extreme solar heating and space weather that is otherwise impossible to capture from Earth.
So whether you are packing your bags right now for a highly planned expedition to the volcanic fields of Iceland, or you're just going to walk out to your driveway in the evening to catch the dust of Comet Swift-Tuttle burning up in the atmosphere, you are now fully equipped to understand exactly what is happening in the intricate cosmic clockwork above you.
And before we go, I do want to leave you with one final thought to ponder regarding that clockwork.
Well, please do. We talked a lot about the mechanics, the orbital speed, and the precise geometry required for a total eclipse. But just consider the sheer staggering statistical luck of our existence.
Oh, so.
Well, the sun's diameter is roughly 400 times larger than the moon's.
Hmm.
But by a pure arbitrary stroke of cosmic coincidence, the sun also happens to be roughly 400 times further away from the Earth than the moon is.
Wow, the ultimate orbital ratio.
Precisely. Because of that exact 400 to 400 ratio, from our perspective down here on Earth, the two most important celestial bodies in our sky appear to be the exact same perfect size.
That is honestly mind-blowing when you really think about it.
It is. If the moon were even slightly smaller or just a little bit further away in its orbit, it would never be able to completely block the sun's disk.
So the path of totality wouldn't just be narrow, it just wouldn't exist at all.
Exactly. We would only ever experience partial eclipses, and the majestic, violent mechanics of the sun's hidden corona would remain permanently locked away from our view.